Thank you, Sharbat. Hello, everyone. So I'll be talking about our work on statistical error compensation-based energy-efficient Beyond-CMOS systems. So as Sharbil introduced, I work with Professor Naresh Shambhag. And this work was done in collaboration with Shashikant Manipatruni, Dimitri Nikono, and Ian Young from Intel. And so our group primarily works on energy-efficient circuits. So our collaborators educated us about Beyond-CMOS devices, and we work on statistical error compensation. So let's start it. So all of us now are aware of energy-efficient computation challenge. So we have these interesting emerging applications. For example, we want very smart watches. We want smartphones that are super intelligent. But that intelligence comes at a very high cost of energy and a compute-intensive nature. And so these are typically battery-operated devices, and they have constrained resources. They don't have high compute power or the energy to spend. So when the application space is getting interesting, at the same time, unfortunately or fortunately, the CMOS device scaling is slowing down. So CMOS device, we relied on its scaling and its efficiency for past 3 decades. Now that is not at the same pace anymore. We know that power density numbers are increasing, leakage component is also increasing, and the scaling node doesn't give as many returns anymore. And also it is becoming vulnerable to the PVT variations. So at one hand, our application space is getting more and more interesting. The second hand, the device which helped us to build better computers now is not scaling as well as it used to. So we need to explore some new techniques, some new system level techniques to achieve energy efficiency. And one such framework is what our group developed was Shannon-inspired statistical computing. And the research in this framework has been going on before I started my PhD. So in Shannon-inspired statistical computing, we treat computation as an error-prone communication channel. Essentially, we allow compute to make errors, hardware errors, in return for it to be more energy efficient. So we say that, okay, let hardware make errors at the cost of very low energy, and then we will develop techniques to compensate those errors. And so essentially we have this error-prone computation where main block is of 85 to 90% of the total complexity. It is operating at low energy, and hence it is prone to hardware errors. Now we want to be able to compensate those errors. One technique what we do is that to be able to compensate these computational errors, we add a small redundant block, which we call estimator, which is about 10% of total complexity. And then we have, which also tries to compute the correct output, but because it is of small complexity, it is not able to compute it correctly. And so it has some estimation errors. And then our compensator is a fusion block, which observes 2 erroneous outputs. One is the main block output, one is the estimator output, and its job is to be able to estimate the correct output Y0, which is unknown. So the basic idea is that you have multiple unreliable observations, and you figure out a way to estimate the correct data of which the unreliable observations are. So to be able to efficiently estimate the correct output, we rely on these 2 fundamental principles. One, because the computational error and estimation error are of different source, they are independent. So we have this error independence. And additionally, we try to shape the distribution of these errors to be different from each other. So here I'm showing the distribution of error, hard computational error is sparse, whereas the distribution of estimation error is dense. And this difference in the distribution allows us to compensate error more efficiently and to be able to compensate the correct output with high accuracy with a low complexity fusion block. So this is the basic overview of this technique. So before I started this work, this technique was, different versions of these techniques were shown in CMOS designs. And so they had fabricated chips in, for example, this is sub-threshold ECG processor, and then this is 256-tap PN code acquisition in 180 nanometer CMOS. So they observed that even though pre-compensation error rates are very high, the P-det they were able to maintain, and they were able to reduce the energy of these designs. Now, given that these techniques were successful for CMOS, the question we asked is, can they help in the Beyond-CMOS space? So as we know, that CMOS scaling is slowing down, there is huge interest in exploring some other devices that can potentially become alternative to CMOS. And here I'm showing that space of spintronic devices one side, electronic devices, and then CMOS. One thing that is clear is that there is no clear alternative to CMOS yet. Most of them are behind CMOS. So on the y-axis there is energy, on the x-axis there is delay, and this plot is for NAND 2. This was a benchmarking study done by this Nikonov and Ian Young, and it was published in JCDC. So most of the devices are not competitive to CMOS yet. And so what we are asking is, can our techniques help these devices? So one such prominent device is the all-spin logic device, which I'm showing here. Since spin logic devices, they use nanomagnets to represent a bit. So they are spintronic system. Instead of using voltage to represent a bit, they are using these magnetization directions of small magnets to represent a bit. And then device researchers figured out a way that you can pass current through this, and then spin torque propagates, and you can flip the next magnet. We won't be going too much details of these devices, but that device is here. So you can ask me that, well, it is too far from CMOS, why do I care? The point is that there are many advantages of these devices. For example, they are non-volatile, they are amenable to scaling, they are very low voltage operation. And so a lot of device research has gone into it, and they have now said that with the device research, the device can be here, which is now close to CMOS. But it is still not better than CMOS. And so the question that we are asking is that, can our Shannon-inspired approach help to move this that can build on top of the device research and make this device competitive to CMOS? And this is the question I'll answer by the end of the presentation, and hope I'll convince you. So what's the opportunity? So to be able to beat CMOS, to be able to gain energy efficiency, we don't have magic wand. We need some opportunity, right? One such opportunity is, so as it turns out, these spin devices, when they are operated at lower energy or lower delay, they start making errors. And so this plot shows the delay versus energy versus switching error rate, which is denoted by epsilon. And so red is very high switching error rate, and green is very low switching error rate. And then interesting observation is that if you want them to be very reliable, maybe do one error in 10 to the minus 14 operations, then they are not competitive to CMOS. But if you say that, okay, I'm able to do error at the rate of 1%, which is 10 to the minus 2, this orange here, then they're better than CMOS, because here on the left side is the lower energy, and the lower part is the lower delay. So being on the left side of CMOS is better. So you can, if you can come up with some technique to operate these devices at higher rate, then you can beat CMOS, because CMOS energy delay curve is here. And today, one-on-one computing, or in general digital computing, requires these devices to be very reliable, and they are very far from CMOS. And so our technique is trying to enable spin devices to operate in this region for them to be able to be competitive to CMOS. All right? So just to start with, for a system level, you need a good model of the errors. And so this, I'm showing a model of these switching errors. These switching errors are basically incorrect bit flips at the output. And because these gates are non-volatile, your bit remains. So there is some probability, which we denote by epsilon, that the final output doesn't flip. And so this can be modeled as an extra XOR gate, where there is a random input. And if this random input is 1, then your bit doesn't flip. Otherwise, it flips. And if the gate makes error only if it is required to switch. So this case accounts for the fact that it may not need to switch. And these error rates are dependent on the gate delay TG. And that the relationship is observed last slide. Okay? So we came up with a way, now given that every gate is making error, we came up with a way to distribute the delays of our circuit such that we can control the output error distribution. And so we came up with two techniques, intra-part delay balancing and inter-part delay redistribution. So because the error rates of the gates is depending on the delay, we came up with techniques to distribute the delays in a given circuit such that our error distribution gets sparse. So key underlying is that if we have a path, you have a choice of giving high delays to these two gates and very low delays to these two gates. So this is the delay redistribution along the path. And if you have a shorter path, you are allowed to make the delay of that gate much longer. And if the delay is longer, then it is operating at lower error rate. So with these techniques, we observed that using these techniques, we were able to shape the distribution of errors. So when the all gate delays are equal, the distribution is odd. But when we apply our techniques, we achieve a sparse distribution, which is easier to compensate for. And so this figure shows the impact of our errors, our gate delay distribution, and the colors. The red is that all gates are in high error, and then after applying our techniques, we see that some of the gates can operate at lower error rates, which helps us to shape the distribution of errors at its output. So now, given that you have shaped the distribution of errors, the question is, how do you compensate for them? So the key compensation block is the fusion block, which takes these two observations, which is one is main block output, one is estimator output. They are the same observations of the correct output with different errors, and its job is to estimate the correct output. And now we have shaped the distribution of error eta to be sparse. If you approximate main block by a low complexity estimator, then distribution of the estimator error is dense. If you subtract these two errors get convolved, and then so the distribution of the eta minus e, or if you subtract ya minus ye, it looks like a convolution between these two distributions. And then from this distribution, you are able to estimate the eta correctly. Because if you threshold it at right places, then you have, with high probability, you will be able to estimate what was the one of the errors. And then you can subtract that error from the observed output to estimate the correct output. These details are more in the paper. And then we observed that this threshold comparison can be implemented efficiently as a tree. So you just subtract these two outputs and then do a bunch of comparisons. And these thresholds are observed from the estimated distributions. You do a bunch of comparisons, and then you have compensated for the error. Okay, so we implemented this system to demonstrate our effectiveness. We implemented a support vector machine classifier to do seizure detection. And so basically, it is a linear SVM classifier. It implements a dot product. You have a W, B, X. I think this is very well known. We are implementing a one high dimensional dot product. So conventionally, you would implement it like this. You will have 120 multipliers. It's a 120 dimensional input vector. You will have 120 multipliers. You have a carry save adder. This is a conventional architecture. In Shannon inspired, as we discussed, we add a small error compensator block, which part of it is estimator, and then part of it is a fusion block, which compensates for the error. And then this red is in the main block. We developed some techniques to be able to reuse part of the main block as an estimator, and more details can be observed in the paper. And so the error compensation overhead is only of 10%. So these are our final results. So on these results, I'm showing on the y-axis, I'm showing true positive rate, which is the accuracy of the system. And on x-axis, I'm showing the average device error rate. And so you can see that error-free ideal, the accuracy is about 90-91%. The conventional implementation falls off immediately at very low error rate, whereas Shannon-inspired technique is able to meet the accuracy even though error rate is as high as 1%. And then we have this Shannon-inspired estimator, and then we compare it with 3MR approach, one resiliency approach, where we replicate the block 3 times. We observe that it gives you only an order of magnitude improvement in the error rate, but again it falls off quickly. And on that plot, so for a fixed error rate, there is corresponding energy. So on that plot, I'm doing accuracy versus energy per decision comparison. And so we observe that even though we are getting 1000x more error rate tolerance, we are able to get only 3x reduction in terms of energy. So this is the conventional energy versus accuracy, and this is Shannon-inspired, our approach, energy versus accuracy. So we are 3x better than conventional. So one thing we observed is that it's typically logarithmic. The 1000x benefit that you get, the energy benefits are logarithmic of your error rate benefits. And we still stay short of 1.7x. So see, we are not able to beat CMOS yet, but we still get a big benefit compared to conventional. So I'll conclude with a short summary. So I demonstrated to you that ASL devices are more energy efficient than CMOS if they're operating at higher error rates, and then they can operate at lower energy. We showed how the Shannon-inspired framework can do the error statistic shaping and then error compensation to achieve the high error rate tolerance, and we achieved 1000x improvement in average error rate tolerance. For the next steps, one possibility is to extend this work to more complex networks, such as deep neural networks. And another one possibility we are considering is that because devices are inherently stochastic in nature, can they help to implement efficient learning algorithms where stochasticity plays a natural role? Thank you. Thank you for your attention. Are there any questions? Yes?
Do you think your technology will benefit like Bitcoin mining?
Bitcoin mining?
Because for Bitcoin mining, you require low energy consumption.
I see.
Yeah.
Wow. So, I mean, the answer is yes, but we have not tied ourselves to any application yet. So we are about that any given computation block, we want to be able to do it as low energy as possible. So I mean, with that, just that in mind, it will help Bitcoin mining. But there might be bigger opportunities in Bitcoin mining. For example, stochasticity might play a role in doing efficient implementation of Bitcoin mining. That's a good thought, yeah.
Any other questions?
Yes?
Actually, my instinct would be no, because randomness wouldn't be acceptable in cryptography. But anyway, my question is about the trade-off between delay, energy, and error rate.
Yes.
Can you say a little bit more about how that's computed, and if that's something that can be generalized to devices in general, or does it have to be for a specific type of device or type of circuit?
Okay, so the approach of characterizing energy, delay, and in more general sense reliability is valid for many, many devices. But the exact numbers and the way we obtain plot is specific to the device we are considering. And I believe it will be specific because it is heavily depending on the underlying physics, which is going to be different for many devices. So our plots are more or less valid for many spintronic devices because underlying physics is similar. But let's say if you ask me for RRAM, then physics is different, but you can still get some plot. But you'll have to research the device, understand the physics, and obtain the plot. Sure?
Any final questions? Okay, so let's thank the speaker again.
Thank you. Thank you.
And this